Okay guys, now we are going to look at the heat transfer on the Carnot steam cycle. So let me write the value of work and heat involved. In this case, this is our W12. This is for the boiler part, which is Q41. This is the condenser side, which is the Q23. Okay, sorry for that. I put it a bit higher. So this is Q23. And then this is our W12. Okay. So again, same on the TS diagram, we are going to say to have the same energy transfer in terms of Q and also in terms of work. Right. Now let us look. In order to solve all these Q and W's, we are going to look at the steady flow energy equation. And the first one is to look on the first process, which is the W12. For W12, we could have the formula of H1 minus H2. And please remember, from here, we are going to ignore the changes in kinetic energy equal to 0. We are going to ignore the change in potential energy. So what is left is just the internal energy and the flow work. Therefore, for W12, we are going to have this type of equation, H1 minus H2. While for the Q23, we are going to have this H2 minus H3. Okay, and while in the Q34, the work input to the compressor, W34, so we are going to have the H4 minus H3, and the last energy transfer in terms of H is the heat supply to the boiler, Q41. So this is, we are going to have the H1 minus H4. And as far as the thermal efficiency for this Carnot cycle is concerned, we are going to look at the general equation, which is the W net divided by the Q in. And in this case, the W net is equivalent to the W12 minus W34, while the heat or the energy input Q in is equivalent to the Q41. So based on this formula, meaning that we need to get all the enthalpies at every state 1, 2, 3, and 4. Alright? So as far as the enthalpy is concerned, the H1 is equal to the Hg at our T1. Okay, and then the H2, we are going to get that from the mixture type of state of steam, which is equal to the HF2 plus X2 HFG2. And the X value, as usual, the X value, you are going to get the X value of 2, the quality or the Dyna's fraction. It's basically, we are going to get that based on what? Based on the entropy. Okay, so this is S2 minus SF2 divided by SFG2. This is our X2, where we know that the S2 is equal to the S1. for the reversible adiabatic expansion process, or also known as the isentropic expansion. So that is as for the H2. And then for the value of H3, we should get first the H4. We can get the H4. The H4 is equal to the HF4, okay, which is the HF at the given temperature of T1. And at the same time, we could get our value of S4, which is equal to the S3. And based on the S3, we could get what is our X3. Once we have our X3, then we will solve for the H3. So this is how you solve using all the enthalpy value. Okay, using the enthalpy value. So for this case, we will get the thermal efficiency of the Carnot cycle by looking at the SFEE. Okay, the SFEE. So next, we are going to look on the thermal efficiency of the Carnot cycle based on the entropy change, or based on the entropy definition, which can be used for the reversible Carnot cycle, or can be used for the all reversible adiabatic expansion and compression process.